So today we're going to talk about free body diagrams. Free body diagrams is a way of representing all the forces that act on an object. And as we move forward in dynamics, it's going to be important to be able to have a visual of the forces acting on an object and in what direction they're in, so we know whether to analyze them vertically or horizontally. So today's goal is to see a couple of different forces that we commonly use, and to learn how to draw a diagram that represents how these forces are acting on an object. So there is the force of friction. The symbol for force of friction is a large or uppercase F with a subscript of a lowercase f. This is the force of resistance that a surface exerts on an object. So the force of friction is present when two surfaces are in contact. And the force of friction is a resistive force, and it happens when an object is moving or when we're trying to move an object. So it's an oppositional force. The normal force is a little tricky. It's something you've never really seen before. The normal force is a balancing force. So this is a force that's exerted by a surface on an object. It's always perpendicular to the surface, and it's in a direction away from the surface. So let me just scroll sideways here, and I'm going to draw a picture. So if this were your desk, right now your book is sitting on your desk. Now, would you say that that book is sinking through the desk? No. The book is staying flush to the top of the desk, which means the desk has to be exerting an upward force on your book, because gravity is pulling your book down. So if gravity is pulling your book down, something has to oppose gravity. That balancing force that opposes gravity is called the normal force. The normal force is always drawn perpendicular to the surface. So here's our surface. The normal force is always perpendicular to the surface. All right? Normal force is always perpendicular to the surface. It points away from the surface. It's the force that the surface exerts to stop the object from sinking through it. So the normal force is the oppositional force that the desk or the floor exerts that stops you from going through it. So that's the normal force, and it's always perpendicular to the surface. We have the force of air resistance. So if something is free falling or moving quickly through the air, then sometimes we have the force of air that's trying to stop that object from moving. We have the force of tension. So force of tension, Ft, is used to represent anything that's like a rope, a chain, a cable. So if you're pulling on a sled by a rope, that's going to be tension. And an applied force is a push or a pull. So an applied force is a push or a pull when you're directly touching the object to exert that force. Before trying to analyze complex situations, it is first necessary to identify all the forces acting on an object. And free body diagrams are going to help us to do that. So in this first question here, we're just going to identify the different forces that we think are acting on an object. So if we have a book, so I'd like you to pause the video, or maybe I'll do the first one with you. So we have a book that's at rest on a table. So we have a book here, it's at rest on a table. What forces are acting on that book? Well, we have gravity that's pulling the book down, and we have the normal force that's stopping the book from sinking through the table. Okay, now I'd like you to pause the video, and I would like you to answer which forces are acting on in each of these situations. Perfect. All right, so here we go. We have a book that's being pushed by a person horizontally to the right at a constant speed. So let's say the book is on the floor and it's being pushed and moving to the right. Okay? So if it's moving to the right, the book is in contact with the floor, so I think there's a frictional force. I am pushing, which means I am applying a force. even though this book is on the floor, it still has a force due to gravity. And it's not sinking through the floor, which means there has to be a normal force in the opposite direction. If we look at the book in the previous question, now we've let the book go. Once we no longer have our hand on the book, there is no longer an applied force. We will still have friction because the book is still moving and coming to a stop. We will still have gravity, and we will still have the normal force, but there will no longer be an applied force. Now let's look at a book that is falling through the air and accelerating downwards. So the reason the book is falling is because of gravity, and as it falls through the air, we can assume that there is some air resistance that happens there. So hopefully you were able to identify the forces acting in each of these situations. Not only do we need to be able to identify the forces, we need to be able to identify how the forces are acting on an object. And the way we do that is by using a free body diagram. So a free body diagram shows the size, the relative size, and the direction of each of the forces acting on an object. You don't need to be an artist to make free body diagrams. You can either draw them from a box or just from a circle, from a little point. So a free body diagram is essential when we're setting up problems involving forces. It identifies all the forces with their directions acting on an object, and it's only representing forces acting on that object. That's important. The free body diagram is only representing forces acting on this one object. Each object will need its own free body diagram. So each force should be represented by an arrow that is directed outwards from the body in the direction of the force. So let's look at the situation here where the box is sitting on the table. I'm going to draw the forces acting directly on the box, and then we're going to draw a free body diagram to the side. So we have gravity pulling us down. And since the box is not sinking through the table or floating through the air, we know that we have a normal force pulling up on the box. The box is not moving left or right, and there's nothing pushing on it left or right, which means there's no force for friction to oppose, which means there won't be a frictional force. So if I want to draw a free body diagram, I start with a dot. I pull my arrow downwards, FG, and now I would like to see the normal force pretty close to the same size as the gravitational force because the book is not accelerating, it's at rest. So if it's at rest, there should be no net force, and the normal force and gravitational force should balance each other out. Let's look at example 2. So this is a free body diagram. Notice it's drawn right from just a point. And we see that we have normal force and gravitational force, which is balanced. And we have frictional force and an applied force. They are not balanced. Since the applied force here is significantly larger than the frictional force, that means we have a net force, and this object will accelerate to the right in the direction of that net force. Okay, your turn. Check your understanding in the following four situations. So give it a try. Try and draw a free body diagram. We've already identified what forces act on the object. Use that information to help you draw a free body diagram. So pause your video and draw those free body diagrams. All right, now that you have those free body diagrams drawn, let's take a look together. So a book at rest on a table. We said that we had the gravitational force pulling us down, and we have the normal force pulling us up. Both the length of the gravitational and normal force should be relatively equal because they are balanced. The object is not floating into the air or accelerating or sinking through the table. A book being pushed by a person horizontally to the right. We identified again the gravitational force and the normal force, which should be balanced. Since the book is moving at a constant speed, the length of the applied force and the length, that's not a very good drawing, oops. The length of the applied force and the frictional force should be similar. Now again, I'm not taking out a ruler to make sure that they're the same size, but visually they should look about the same size. Now see, the book in the previous question is let go. So when we let go of the book, that means we are going to lose the applied force. So we still have gravity pulling us down. We still have the normal force pulling us up. We no longer have the applied force, but we do still have the frictional force. And we see that we have a net force to the left, and that makes sense because the object is slowing down to a stop. Finally, in D, the object is falling through the air, and it's accelerating downward. So that means the downward force of gravity has to be bigger than the upward force of air resistance. Okay, now I would like you, I've already distributed worksheet 2.1.3. I'd like you to do questions 1 to 3 on worksheet 2.1.3. Okay, so questions 1 to 3. So you have the questions and the solutions. I've already distributed them. Please take the time to do these questions and check your answers to make sure that you're doing them properly.